So let's look at some more examples where we have to decide which mechanism the reaction is going to follow. Our first example, we have a secondary alkyl halide, meaning we can do any of the four. So we have to look at our reagent now. Potassium is a cation, hydroxide's an anion. We have a strong base, strong nucleophile. So because of that, we are looking at our SN2 and E2. Now, the heat is going to help us decide that E2 is most likely going to happen. Without heat, you probably get a mixture of both, but adding heat is really going to enforce the E2 elimination. Now, whenever you have two chiral centers here, you have to pay attention to the stereochemistry, the position of the leaving group, the bromine, and the hydrogen that is on the beta position. Now, in order for the elimination to occur in an E2 fashion, those two have to be anti-periplanar. In other words, they need to be in the same plane on opposite sides. So what we're going to have to do is kind of rotate this molecule, bringing the bromine forward, and that methyl group is going to go as a dash. On the other side, we have to bring this hydrogen forward, bringing that methyl group still a wedge but down here, and the ethyl group is going to be a dash. Now we have the bromine and the hydrogen in a position to where our base can remove the hydrogen as the bromine leaves. And when that happens, we're going to form a double bond, and anything that is a dash is going to be on the same side of that double bond, our methyl and ethyl group. Anything that's a wedge, this hydrogen that's not shown currently, and the other methyl group are going to be on the same side as well. And so here we get this specific stereoisomer. We will not get the double bond like this for an E2 elimination. That is because with E2 it's a concerted process, and it happens when the hydrogen and the bromine are anti-periplanar or anti-planar. Basically, they're both in the plane of the board and going opposite directions. Now the other reason too why we eliminated that way is we have a mono-di-tri substituted alkene. If we eliminated to this other beta position here, so there's our alpha carbon with the leaving group, there's a beta carbon, there's a beta carbon. If we eliminated up here, we would only get a mono-substituted alkene, which is less stable. This is the Hofmann product, and it would only occur if we used a bulky base. Hydroxide's a small base, so we're going to get the thermodynamic Zaitsev product. In the next example, we have a primary alcohol. The alcohol is not a good leaving group, so we have to make it a leaving group, and that's why they add HCl. The HCl is going to protonate that alcohol, making the leaving group water. Water is a decent leaving group, and if this was a secondary or tertiary alcohol that we protonate, we could potentially do an E1 or SN1 where the leaving group goes forming a carbocation. But because we have a primary position, we can only do SN1 or SN2 or E2. And when we protonated, we generated Cl-. Cl- is not a base, so we're not going to do the E2 elimination. Instead, we have a nucleophile. We're going to do the SN2 and kick out water and put our chlorine there. Last, we're going to do something similar where we have our alcohol. This one is actually secondary. We're going to add an acid, which is going to make that alcohol a leaving group, and we're also adding heat. Heat usually an indicator we're doing elimination. We have a secondary alkyl halide. secondary alcohol, meaning that we could either do potentially E1 or E2. Because we're not using a strong base, usually in acidic conditions, we're going to favor the E1 elimination. We're forming a carbocation. So the first step, we protonate our alcohol to make water as a leaving group. That is going to leave, and we form that secondary carbocation. I kind of rotated it there, so let me draw it in the same orientation so it's easier to see. Now you would expect the elimination then to occur where I eliminate to the more substituted side, giving us that product. But technically what's going to happen is that's a secondary carbocation. Over here would be a tertiary. We would actually do a hydride shift. And so you always have to pay attention to those hydride shifts. Anytime you form a secondary carbocation, look to see if there's an adjacent position where you can shift a group over, forming a tertiary carbocation. Now when we do the elimination here, again, you're going to favor the Zaitsev product, the more substituted, more stable product, because we're heating this up and we're using acidic conditions. And regardless of whether you notice the rearrangement or not, you actually get the same product. But keep in mind that's not always true. So whenever you do an E1 or an SN1, pay attention to the cation. Will a rearrangement occur? Do I need to consider other potential products? So the first example we decided was E2 because we had a secondary alkyl halide with a strong nucleophile base, but we heated it up, indicating E2. Because it was E2, we had to arrange the molecules so that the hydrogen and the leaving group bromine were antiplanar to each other, and then we eliminated, giving us a specific stereochemistry. The next one, we have an alcohol in acidic conditions. We protonate the alcohol, making the good leaving group. And then when we protonate the alcohol, we have a good nucleophile chloride, which will do an SN2 because we had a primary alcohol. If we had a secondary or tertiary, we would have SN1. Secondary would actually do either SN1 or SN2, but a tertiary would only do SN1. And then last, again, secondary alcohol, acidic conditions, we make our leaving group, which is water. The leaving group leaves because it's secondary alcohol, meaning that we can form a carbocation there. And we don't have a strong base for acidic conditions, so we're usually going to favor a lot of times the E1 process. And so then we get the carbocation, we do our hydride shift, and then we do our elimination where we remove an adjacent hydrogen, forming our double bond. For this one, again, it didn't matter whether you did the hydride shift or not, you'd get the same product.